that sound good? Everybody settled in? Welcome everybody. It's my pleasure to welcome you all to the 2013 Eminent Scholar Lecture Series, which is hosted by the College of Marine Science and the United States Geological Survey and graciously supported by the Tampa Bay Times. I want to extend a real gratitude to them for their support for our lecture series. It's been great. Today we're going to have a really exciting lecture series with four permanent international scholars focusing in on some of the most important aspects of societally relevant issues to the earth and ocean sciences involving climate change, ice sheet melting, potential sea level impacts, as well as biological impacts. As you know, the ice melting and glacial melting in general and global climate change is a topic that's been well attended here and well represented here in the College of Marine Science. Just to name a few of those that are working in polar systems: Amelia Cheminel, Don Chambers, Gary Mitchum, Bob Byrne, Kendra Daly, Jose Torres, just to name a few. But one of the names that is really missing in this list is our dear friend and our science colleague and a gentle soul that is sorely missed, Professor Ben Flower. As many of you know, Ben passed away July of 2012, just this last year. It was soon after that event, in the same auditorium, that we had a ceremony to celebrate the life of Ben Flower, his heart, his friendships, his generosity, his discipline, and his passion for science. That celebration of Ben was such a moving moment, I think, for many of you that were there. I oftentimes still get choked up over the whole thing, and I think I can speak for many of us that he is still in our minds and really permanently seated in our memories. One aspect of Ben's life that was left to be remembered and respected in the future was the scientific research in paleoceanography, climate change, and today we are here to hear about some of that. Again, here's a couple of pictures. Perhaps, could I get the lights dim?
Yeah, terrible renditions.
I want everybody just to...
Hope they can see my slides.
I know. It's
No? Okay, but I'm just going to do it for a second so our audience can see a picture of Ben, if that's a possibility.
Yeah.
And again, well, it may
No.
not work
That's
as well
not
as
good.
we'd
It's
like
the
it to.
projector.
It's the
Ben was a
projector.
very gentle
I have a
soul.
better one than that.
And
I took that photo.
It's on my fridge. You gave it to us.
Yeah, I took
Ben's
it.
research
That's
in
in.
paleoclimate,
It's in Portugal.
ice melting, really was his legacy. And Ben had been studying ice melting and glacial melting and meltwater and climate change since the late 80s. There you go. These are just a few of Ben's research and literature in really preeminent journals, really identifying that this has been a real focus for his life. We're going to hear about that by many of our speakers, both looking at glacial melting, the topic for this lecture series, glacial melting past, present, and future, how much, how fast, and what impacts. And again, I'd just like to extend this as a tribute to Ben Flower. And we're going to have his four speakers, and Amelia Cheminel will introduce our first speaker.
Thank you very much for coming. So it's my pleasure to introduce our first speaker, Dr. James Kennett. Jim got his PhD in geology in Wellington, New Zealand, before the dawn of time. And
Well before.
since then, he has been a professor at many institutions, including up north at some place called Tallahassee that we may know about. And he was also a professor at the Graduate School of Oceanography in Rhode Island, and many of you probably knew him then. Then he moved to Santa Barbara, where he was the director of the Marine Science Institute, and then also a professor at, in the Department of Geological Sciences, or Earth Sciences, whatever they like to call themselves now. Jim is a member of the National Academy of Sciences. He's an AGU fellow, AAAS fellow probably, and everything else under the sun. But most importantly, Jim was Ben's PhD advisor, and he's So I'm extremely excited that he was able to make it, and he's going to talk to us today about the YDB Cosmic Impact at the cause of Younger Dryas, climatic, biotic, and cultural anomalies. And I originally had a much shorter title than that. So, great pleasure to introduce Jim.
Thank you, Laura. Okay. So, well, thank you very much for coming. It's a real privilege for me to be here in support of a tribute for Ben Flower. The talk, I will be, the title of the talk is the YDB Cosmic Impact as cause for the Younger Dryas climatic, biotic, and cultural anomalies. And so the talk basically is about the ever enigmatic Younger Dryas cooling episode and the forever contentious, controversial YDB Impact Hypothesis. The Younger Dryas episode, I'll just get started here. The Younger Dryas episode was a sharp cooling that occurred about midway during the last deglaciation, coming out of the last ice age. It began at pretty well exactly 12.9 thousand years ago. Half the ice in the Laurentide ice sheet in the northern hemisphere had melted, so sea level had come up about 60 meters, had about 60 meters to go. So about midway during the deglaciation, we had the sharp return to near-glacial conditions that has been forever anomalous, why this occurred. And so there's been various ideas about this. Basically, I'd like to make the point, and I will say two things before as I start here. I'm going to show you a lot of slides that have a lot of detail, but most of them are basically cues for a step in the thinking relative to this hypothesis about the Younger Dryas, and I've sketched down some of for those of you can see, sketched down more or less the direction in which this talk will go. So I'm going to be talking about the cooling, and it was the cooling anomalous, and then the continental plumbing shift. But basically, the question is, was the Younger Dryas cooling an anomalous cooling? As far as I'm concerned, it is, because it occurred during there's the deglaciation coming up here. This is the termination one. There's the Younger Dryas in here, and it occurred near the peak of this precession. This is precession, or if you like, northern hemisphere solar radiation receipt, and so it's occurring near the top of the peak solar radiations of the northern hemisphere, and it's totally unlike nearly all of the major glacial, deglacial warming and cooling trends, because it occurred during a time of a major cooling occurred at a time of significant, what should have been significant warmth. And when you go back to the other terminations, there's nothing quite like that. And even in termination 3, which is about 250,000 years ago, this cooling here was occurring actually during the base of cooling and the precession. So this is not analogous, as Chang and others have suggested. This is in my opinion, no way analogous to the Younger Dryas. So what I'm saying here is that the Younger Dryas, based on this kind of data, is anomalous. Another way of looking at this is to look at the methane record through the Lake Quaternary, and when we go through the glacials, interglacial and glacial cycles back to about 800,000 years ago. These are interglacials here as we proceed back through time. Because of the close association between atmospheric methane changes and climate, we're able to compare these records and determine where if there was a Younger Dryas type methane drop. There's the Younger Dryas, there's the methane drop. This is methane, as revealed by the methane changes. If any of these such events occurred during deglaciations in the previous deglaciations, and if you step on back, basically there are none. You step on back through 800,000 years. There's nothing that's analogous to the Younger Dryas, which again is suggestive that the Younger Dryas is in fact an anomalous cooling episode during a deglaciation. Now, okay, so as far as we're concerned, the Younger Dryas is anomalous as a climatic event. It's quite unlike any of the others. So what happened to the Younger Dryas? Basically, the onset is quite well known because of the Greenland ice sheet record work. This is some studies by Stephenson, the Danish worker, from the grip record. And here's the Younger Dryas onset. The climatic change that occurred at the onset of the Younger Dryas, which is at 12.9 thousand years ago, it took 1 year. The atmospheric shift was 1 year. The initiation of cooling occurred then. There it is there. So that's a 1 year, call it a transition. It's a sharp change. Then the cooling itself that resulted from that through feedbacks, through climatic feedbacks, took about 100 over 100 years. So and that's what would be expected because this is reflecting the climatic feedbacks that increase the cooling that marked the Younger Dryas. But the climate change itself took place in 1 year. And this is supported by numbers of papers in Germany and in North America where they have annual valves, and the major shift in the valve thickness, which is reflecting the atmospheric change that marks the beginning of the Younger Dryas, occurs in 1 year. So the evidence suggests that this was an incredibly sharp climatic change. Now, this is a tribute to Ben. I took this photograph actually during a Paleoceanographic Congress in Portugal a few years ago. And I want to bring in Ben here now because Ben he worked extensively, as many of you know, and some of you actually co-worked with Ben on his papers. Here are his papers that deal with or touch on the Younger Dryas climatic and oceanographic changes. He never got into the YDB Impact Hypothesis, but I must say that he always had an open mind about this when I spoke with him. But basically, I'll tell you how he got into the Younger Dryas because this was not part of his PhD thesis. When he wrote to me when I was at Graduate School of Oceanography in Rhode Island, and he said, "I'd like to work with you." I said, "Yes, you can work with me, but you're going to have to work with me in Santa Barbara because I'm moving to Santa Barbara." And so he said, "Okay, I'll come to Santa Barbara." So that's what happened, and he was my right-hand person who helps me set up my labs. So I said, "Look, I really tried to get my graduate students doing research as soon as possible." I said, "Look, Ben, I'd like you to help me with the Younger Dryas. I've got this work going on the Younger Dryas, and I need some help. You work on that, and we'll figure out what you're going to do for your PhD." As it turned out, he worked on the Miocene, but so he began the work, and the first of all papers that he was involved with as a co-author was the paper with Wally Broker, which was in Nature, on the relationship between the plumbing shift, the continental plumbing shift, with the onset of the Younger Dryas, and the effect it had on the meridional overturning, oceanic overturning, or the MOC, or if you wish, the conveyor circulation. And that was a classic paper that Wally Broker championed, and has been in a sense sort of the basic hypothesis or trigger for the onset of the Younger Dryas up until this time. So that's how Ben got into the Younger Dryas, and of course he continued with that work when he moved here to the University of South Florida. Now, we started this work actually on the plumbing shift. I did a paper with Nick Shackleton in the middle 70s, published in 1975, in which we discovered the meltwater spike in the Gulf of Mexico and found the termination of that occurred at 12.9, believe it or not. We dated it at 11,000 radiocarbon, which is equivalent to 12.9 thousand years ago. And we suggested then, Nick Shackleton and I, that there was a plumbing shift, a continental plumbing shift, that took away the meltwater from the melting Laurentide ice sheet and Lake Agassiz up in here, took it away, rather rapidly and threw it out into the Gulf, through the Gulf at St. Lawrence. And that started this whole thing. You can see some of the arrows going here in terms of meltwater directions. And this is a work of Ben and his colleagues, students and colleagues. He worked this up at much greater detail with much better chronological resolution, and basically came up with this big meltwater shift here in the Gulf of Mexico at 12.9 thousand years ago, this being the meltwater spike in here. The other thing that Ben and his colleagues did was to show that during the late Quaternary, the earlier warming episodes, the so-called Dansgaard-Ushka cycles, climatic cycles, as shown here, all these oscillations that occur well established and well documented in the Greenland ice sheet, that these did not operate the same way as the Younger Dryas. He did that by doing they did this by doing excellent correlation work between the climate work in the Gulf of Mexico and comparing it with Greenland. And so the main point is that the Younger Dryas still stands out as an anomalous event when you get to all these kinds of climatic oscillations, warmings and cooling that preceded the Younger Dryas. They have superficial resemblance to the Younger Dryas, but they did not operate as the Younger Dryas. The Younger Dryas seems to have been the only major plumbing shift that occurred during the late Quaternary in North America. It's a standout event again. And these operated, without going into detail, these operated in a different way. And that was a major contribution also from Ben Flower's lab with him and his students and his colleagues. Now, so basically what we have then is, in terms of this plumbing shift we're talking about, there are different directions of meltwater outbursts and floods, if you wish, coming from the southern part of the Laurentide ice sheet and, of course, Lake Agassiz, which was an enormous proglacial lake. And these outlets, you can see there are various outlets. There's the Hudson, the St. Lawrence, there's the Hudson Bay, and of course there's the Mackenzie into the Arctic. There's been a lot of debate as to where the meltwater went, because it did get cut off from the Gulf of Mexico at 12.9, and it had to go somewhere. Jim Teller has argued for years that Lake Agassiz shows a sudden drainage. There was a sudden drainage of this huge proglacial Lake Agassiz at 12.9 thousand years ago. So the water had to go somewhere. And there's been a lot of debate, a lot of arguments about whether it went east, into the North Atlantic, and into the north. And this is important because of the way that it affected ocean circulation, as shown in this cartoon. So there was indeed a major ocean circulation switch at the beginning of the Younger Dryas, an abrupt decrease in the ocean meridian overturning, if you like, or the oceanic conveyor, as shown by this cartoon. It's represented by a host of lines of evidence now. This is radiocarbon ages and with water depth through time in the North Atlantic, which shows this key change in the Younger Dryas. Which is reflecting this change in ocean overturning. And so that's been the favoured hypothesis relative to the triggering of the cooling for the Younger Dryas, because of the effects that this switching on and off, if you wish, of the conveyor has on the climate of the North Atlantic, in fact, the Northern Hemisphere. So there's no question at all. There's a strong relationship between the onset of the Younger Dryas, the plumbing shift, and ocean circulation. Those are all strongly related. They're all part of this hypothesis theory. But the question, of course, is: was there something else that triggered these happenings, if you like, as we're down to here? And of course, there was feedback. There was this major feedback through cooling because of the oceanic shift, and of course of the inertia that is created for the longevity, if you like, of the Younger Dryas cooling episode, which in fact did last 1,000 years once it started. There was quite a inertia in that cooling episode. So basically what I've done, and I'm not going to go into any detail because it's insufficient time because I have so many different topics to talk about here, is that what I've done is I've gone into the literature, something like a hawkeye, and I've tried to look for evidence of outburst flooding, salinity changes, melting of ice margins and so forth. And in fact, when I do that, and it keeps increasing, there is without getting into the detail, there's a substantial body of evidence that's building. There's a lot more to go, I agree, because it does require high resolution, quality coring sequences to get at this problem. There is a growing body of evidence that there was a widely distributed flood outflow, if you like, from the melting Laurentide ice sheet. The arguments that are in the community that it's going east, no, it's going north into the Arctic, no, it's coming out of West Greenland to the east of Greenland, to the west of Greenland. As far as I'm concerned, they're all correct. Basically, what this is showing is that there was a pervasive destabilization of the edges of the Laurentide ice sheet and of the effects it had on the surface salinity of numbers of ocean basins that are adjacent to these particular parts of the melting Laurentide ice sheet and of the release of water, if you like, from these vast proglacial lakes. So there's the list. There was a recent one, relatively one of Kennett, for instance, in West Greenland, which is up in here. It's not actually shown. It's right on there in the Labrador Sea. There's actually a very strong negative oxygen isotopic peak right there at the Younger Dryas, strongly suggestive of a superficial low salinity lid in the Labrador Sea, right there at the YDB boundary. This one here I happen to like. I'll show you a couple of examples only. This is a Spielhagen's work of 2005. It's in the laps of sea in the Arctic, and there is the oxygen isotopic record. There it is there. So this is oxygen isotopes plotted. And there's the onset of the Younger Dryas there, I've marked. There it is. There's the equivalent in the GIS2, the Greenland ice sheet. And look at this peak in here, this very negative delta 18 peak, just published some years ago by the German worker Spielhagen. And this is in the Arctic. And I think I would predict that this he happened to have a very good core with carbonate throughout, except you'll notice there's a little gap in the pachyderma record. This is based on a surface-dwelling foram called pachyderma, and we think, in fact, he suggested that the salinity got so low, or the ice got so thick on the surface that there were no planktonic forams at that time, just for a brief time during the Younger Dryas. So here's this one remarkable low salinity peak in the Arctic, which I would suggest is pretty pervasive. Here's another one that recently came out for the Llama Nosgoth Ridge, which is really pretty well right close to the North Pole. And let's see, this is from Knott and Hilaire Marcel, Canadian or Quebecan workers. They've got a core close to the North Pole, and basically, the importance of this, it's an isolated ridge topography, and this is important because if there's outburst floods, as demonstrated by the sediment characteristics, you have to keep in mind that this is an isolated ridge surrounded by deep basins. So somehow the sediment has to get out, and lo and behold, what you have is right at the onset of the Younger Dryas, here, you've got this increased peak in dolomite. It's actually a fine-grained dolomite, and it peaks on up into the Younger Dryas. And the only source of dolomite in the Arctic can be coming from Canada. So this is suggesting a major outburst of melt materials carrying sediments by some mechanism, maybe through either sea ice rafting and nepheloid layers, out into the North Pole region from Canada. And so this is, again, suggestive of a big event. Okay, so basically I've only been able to show you a couple of examples of the evidence for major outburst flooding, and the evidence suggests that it is circumlaurentide ice sheet. It is not only one particular outlet. It's quite pervasive, again suggestive of a major event. Now, if this is so, that there was a lot of if there was a surge in, if you like, in flow of ice to the and meltwater to the oceans at the onset of the Younger Dryas, you might expect to see some evidence of sea level change or sea level rise. This is more speculative because of the relatively low resolution, but it's some work of Bard and others. And basically, this is their plot. Their primary plot is in Tahiti, the coral reef sequences of Tahiti. And what they do is they suggest that there, in several locations there was a little jump up. This is their plot, not mine. It's a little jump up in sea level, which they calculate at about 3 meters, which would be in about 100 years. And this is from the work of Bard. There's some suggested support from Edwards in New Guinea. Again, that is more speculative and needs, because of the very high resolution needed to resolve something like that in the sea level record, it remains at this point suggestive that there was indeed a little jump up in sea level right at the onset of the Younger Dryas. But that's something that needs further work. So basically, that's the story I have so far on the meltwater flow and the associated changes in paleoceanography. What I'd like to do, just summarize that the rest of the talk is about what actually happened at the YDB, and the bottom line is a lot happened at or very close to 12.9 thousand years ago, the onset of the Younger Dryas cooling episode. Now, I've already talked about changes in continental hydrology and the climate and the ocean, so that I've already talked about. There was evidence of increased biomass burning, both in the Greenland ice sheet and in the terrestrial sequences on land. This is disputed, but we argue strongly that there is evidence of major biomass burning at the YDB. There's the deposition over wide areas of a black layer at this time, at the very Younger Dryas period. This was the time of an abrupt extinction of many or most of the North American megafauna species. There was a crash in bison populations and a resulting genetic bottleneck that is known. There's evidence of genetic bottlenecks and numbers of surviving animals. And there are evidence of migrations in surviving animal populations. In terms of the vegetation, there is evidence of a major broad continental vegetation disruption and migration that I'll show you. And then there's also evidence of significant change in human culture and human populations, and also in a human genetic bottleneck based on the molecular work by the Berkeley group of Schroeder and others. And in fact, in California, there's an archaeological gap. If you talk to people like Terry Jones, basically he will say there is no strong evidence or any evidence of human population after the onset of the Younger Dryas in all of California. He has not found any evidence of humans in the early part of the Younger Dryas episode. That's for several hundred years. And then the archaeological evidence begins to come back in the later part of the Younger Dryas. So, okay, I'm going to now talk about the megafauna, which is something I have a long-term interest. I got interested in this when I was about 12 years old. I thought then, as a young 12-year-old, coming from New Zealand, I thought that these animals, many of them are icons, of course, became extinct because of human overkill. I've since changed my mind on that. But that is obviously one of the hypotheses that's being debated, as well as straight climate change. But basically, many of these animals will be familiar to you, of course. There's the mammoths and the mastodons. There's all the American camels became extinct, the dire wolf, the American lion, the numbers of carnivores, including cheetahs, giant jaguars. This is a short-faced bear, which was a monster of a hypercarnivore, and I don't know how humans could have dealt with that, frankly. Giant armadillos, the saber-toothed cat, giant beavers, all the horses became extinct, and of course the giant ground sloths, and of course the bison. The giant bison was replaced by the more modern bison, which is the one that we see, which is the American icon on coins and stamps. So basically, when did these animals become extinct? There's been a long suggestion that they certainly are close, very close to the onset of the Younger Dryas, but some dribble through, and so there's speculation that these things may have survived. But so you have to look at the stratigraphic evidence and also the dating, which is ever increasingly demanding, because radiocarbon dating is very difficult. But basically, I just want to inject here Darwin. Charles Darwin got it right, at least in the various hypotheses during the voyage of the Beagle when he was digging the South American megafaunal fossils in Argentina. And in 1845, the voyage of the Beagle, there's 7 pages in his journal. They make very interesting reading, if you like to read Charles Darwin. But he did recognize the existence then of the American. They knew about the American megafaunal extinction. They knew these animals had lived and has since become extinct. This influenced his thinking about past life and evolution. And he knew that it was a very young extinction, and that, believe it or not, it was since the last cooling. I don't know how he knew much about the last glaciation or cooling, but he said it's occurred since the last cooling. It's in the book. And he considered, this is the important thing, he considered that there were various catastrophic causes. There were 3 hypotheses: catastrophic cause, climate change, and human cause. Those are the 3 hypotheses he posited in the voyage of the Beagle. And these are the 3 that are primarily argued, or have been argued. One or the other, or some combination. He also he dug out a horse tooth. He was able to show that this was actually a fossil horse tooth, and it wasn't a modern one. And he did recognize that the horse extinction had occurred over the Americas, both North and South America. Now, I mentioned horses. I think this is important because of the perspective of what the YDB boundary means in terms of extinction. The megafaunal extinction was a major event. It's underrated. It's a huge event in the history of the American continent and the South American continent. And this is exemplified by horses, because the focus of horse evolution is North America. Horses have always been on North America since the Eocene, about 55 million years ago. There's never been any break in horses' evolution or the presence of horses in North America, except for when? After 12.9 thousand years ago until 500 years ago, when the Spanish brought them back, the conquistadors. And so there's that one gap, and that's the only gap that's known when there were no horses. So there's no phylogenetic break in horses and horse evolution. So that the important thing here is it's showing how important this extinction is. And I frankly don't believe that the humans knocked off all these horses, even though they did overlap, of course, with humans. That is it's a simple thing to anticipate. So basically, what is the stratigraphic evidence and chronological evidence for the extinction of these animals? Well, basically, you have to look at the first-class sequences, and one of these is at Murray Springs in southern Arizona, where I've gone and collected. And basically, much of this is Vance Haynes' work. He's well known for it at the University of Arizona. Basically, you've got the extinction of mammoth, horse, camel, dire wolf, American lion, and the great bison. They come right up These animal skeletons come right up. These have been very well excavated in the San Pedro Valley for years, and they become extinct right there. And then they're basically overlapped by or shrouded by this black mat, this black layer. And at the base of the black layer is an even more darker layer that is in fact what we call the YDB layer. And this is, I'll tell you in a minute, it contains this exotic material. So basically we have a straight stratigraphic information. You can try, well, I don't know of any clear evidence of these kinds of animals up in here, anywhere. There are some publications that suggest that there might be mammoths in the later Younger Dryas. This is possible, I suppose, but they're usually not in very good stratigraphic context, and they're not well dated. In other words, they're not credible. This is not credible evidence for their younger age than 12.9. And in fact, Haynes, as you'll see here, Haynes wrote in 1998, the sudden extinction of the Pleistocene megafauna would be dramatically revealed by explaining that all were gone an instant before the black mat was deposited. So he recognized this after all these excavations. And he has, so I better move on. So there's the black mat, and that fact is shrouding a mammoth tooth there. There's the black mat. You can see it a little better. The light is not optimal here. And there's, again, it's not optimal. The light is not optimal, but this is a fully articulated mammoth being excavated. And you can see, I hope you can see, this black layer. That is the black layer shrouding the mammoth skeleton. This is the characteristic of the deposition of these extinct megafauna in San Pedro Valley, and is well written up by Vance Haynes. Now, so what we've done, Douglas and I, my son is an archaeologist, I should mention, and I didn't say this at the beginning of the talk, I have a bunch of reprints just to show the different papers that the YDB Impact group has published. What I'm presenting is a group effort. I think we have up to 50, almost 50 authors now that I've collaborated with in various publications. So this is what I'm presenting is very much a group effort with many different kinds of specialities represented. I have a couple of authors that I strongly work with, is Alan West in Arizona and Ted Bunch in Arizona. And then I work with others like my son Douglas, and Wendy Walvick in Chicago, and so forth. But there's so many I can't mention all their names. But basically, in terms of names, this is a plot of the most credible ages, youngest credible ages, radiocarbon ages, for the extinction of these megafauna, or numbers of these megafauna. And so this is for 16 of the 35 genera that became extinct. Large numbers became extinct. Nearly all of the megafauna in North America were wiped out. It also includes some species like the dire wolf, the saber-toothed cat, and so forth. Basically, plus or minus 100 years, the extinction of these animals is at the base of the Younger Dryas at 12.9. And it includes, and these are plotted in terms of their relative abundances in the record. So horses are very common, and mammoths, mastodons, camel, all the North American camels, some of the ungulates and tapirs and sloths, and so as you go up, the short-faced bear up here. So anyway, these become less abundant as you go up, and so when the most abundant of the animals, where the fossil evidence is best, they're at 12.9, plus or minus 100 years, because that's controlled by the limitations of the radiocarbon dating. We've used a certain formula as to what ages are compelling and what ages are not, and we're strict in what we use. And so, so basically that is strongly suggestive of an abrupt extinction of the megafauna at that time. It includes the mammoth, the mainland mammoth, and also the Pygmy mammoth. The Pygmy mammoth is that little mammoth that lives on the Channel Islands in Southern California. It was isolated on these isolated islands, and the youngest known age of the Pygmy Mammoth on the Channel Islands is 12.9. There's no younger dated Pygmy Mammoths on the Channel Islands than 12.9 thousand years ago. Now, so basically now we'll move to the discussion on the YDB Impact Hypothesis and what actually happened, and the rest of the talk is on that. And I'll have to move quite quickly. Right, Amelia? Basically, what we've been doing is we've been chasing around the North America and Western Europe, Northwest Europe, and also now extending our work even into northern Syria, looking for a layer, the YDB boundary layer. This is here, and as I mentioned, is often, but not always, associated with black mat. And what we found is an assemblage of exotic materials in this thin layer, which is usually only a few centimeters thick. It can be thicker or thinner, depending on the sedimentological conditions. And what we found is a whole range of exotic materials, including nanodiamonds. This is Murray Springs. We have a nanodiamond peak at Murray Springs, right there in that layer there. So suddenly I found myself working in material sciences, which I never ever thought I would work in, and in the last few years, and it's been very interesting because UC Santa Barbara has a very strong material science group in their engineering school, and it's been very nice to work with those. It's been very helpful, those people. So anyway, there you have it. So there's a nanodiamond peak. There's also, as first discovered by my colleague Alan West, who went to Murray Springs first, there was a major peak in impact spherules. You can see there's a particular pattern there for using the SEM scanning electron microscope. This is indicative of a melted spherule that is suddenly cooled or quenched. And there it is. That's a typical impact spherule. I'll show you more later. But anyway, that is also a peak right there in the base of that black mat, just on top of the extinct mammoth fossils in Murray Springs. We have carbon spherules, also at the YDB layer. I've got some carbon spherules here, if you like, with a magnifying glass later, if you like to look at them. They are made of carbon, and in fact, this is the first material we actually discovered nanodiamonds in. So when you look inside these, you work with a high-resolution transmission electron microscope, and I'm afraid you can't see the resolution, but you can see these little black marks in here. Those are nanodiamonds. And so we got a whole range of nanodiamonds. So we got into nanodiamond work, which has been quite exciting because we have four allotropes, or species, of nanodiamonds that we have been tracing with our high-resolution TEM work. And the first nanodiamonds we ever found was actually inside these carbon spherules, which are produced as a result of impact in the interface between the continental, the terrestrial biota, the carbon biota, and the impactor. These actually are produced out of the gases that occur as a result of the wildfires and associated with high temperature impacts. Now, so there's a list of some of the different kinds of proxies that are characteristic of the YDB layer, and there's no time in this talk, obviously, to go through and talk about all of these. But our co-authors have contributed in various ways towards the understanding of these materials in the YDB. So what our favorite hypothesis at this time for the YDB impact hypothesis, if you like, is that there was a fragmented comet that intersected the Earth, and that this is like the Schwarzman-Wachmann comet. This one consists of about 100 major fragments and multiple smaller ones. And what we are suggesting, although this is obviously very much open for further data, is that the Earth was intersected with such a cometary cloud, and And so the evidence we have cannot be explained by a single impact. It has to be explained by multiple impacts and probably multiple aerial impacts. Most of the energy release was actually in the atmosphere, and most of these would not be crater forming, much like the Tunguska type impact about 100 years ago in Siberia. So far, the ejector field we have for the YDB is here. That's the known ejector field of all sorts of materials in these sections that we've studied. I compare this, for instance, with the Australasian tektite field, which is that one. And that was 780,000 years ago. This one was 12.9 thousand years ago. But this is, as the work continues, this ejector field seems to continue to grow. So, okay, now we're on nanodiamonds. I'm going to show you some data on nanodiamonds really quickly. The main point is that we've been able to, through an enormous amount of work, requiring an enormous amount of transmission electron microscope work, which is required to identify the nanodiamonds quantitatively, is that we were able to define believe it or not, a YDB nanodiamond datum. So I'm a stratigrapher, and I never would have ever thought that I'd be talking about a datum that was defined by an abundance of nanodiamonds. But that's indeed what we have, and that is what I propose we have, because that is the data. Okay, and so I'm just going to show you some really quick examples. This is an Arlington Canyon and on the Channel Islands. That was one of the early sites that we collected. This is not, the photograph is not showing up very well here, but there's the YDB, the black layers down in here, the YDB, and really quickly we were put onto this site by a colleague, James West, who's a palynologist at UC Davis, and he told me, this is several years ago, he said, Jim, I have this site, I have a sample that I found in Santa Cruz Island, and it has these black spherules in it, because he was looking for pollen. And he said, are you interested? I said, yeah, but what's the age? He said, well, it's 12.9 thousand years. So I said, we'll run an expedition. So we ran an expedition, and we sampled up on the sequence, and that indeed is the Younger Dryas layer. It is full of nanodiamonds, magnetic spherules, carbon spherules. It's full of charcoal, evidence of major wildfire, and so forth. And so that was, in fact, the first place that we discovered hexagonal diamonds. This is a transmission electron image, well, these are, of this is high-resolution TEM work. You can see these lines here. That's the atomic lattice. Each one of those dots is an individual atom. So you're actually looking at the atomic lattice, which can be measured in angles, and you can determine through crystallography what these crystals are. And these are indeed that's a hexagonal diamond. That's important because, the other name is Lonsdaleite, which is the University of London, Lonsdale. Discovered this crystal, this particular allotrope of diamond. It was Lonsdale, named after her. And there you have it. It's important because there's no other known location. The only known Lonsdaleite on Earth is associated with meteorites and known impact craters. It is not known naturally in any other way. It's basically got a hexagonal structure, and unlike the cubic structure of all the other diamond allotropes. And this is all the kinds of lines of evidence that are used, without going into it, for identifying correctly, and we maintain, in most cases, we are correctly identifying these nanodiamonds. There's all sorts of multiple approaches you use to make sure your taxonomy is correct with the crystallography. Actually, this is Hall's Cave, as yet not written up. I'm doing it with Tom Stafford and others. And basically, Hall's Cave in West Texas. There's the boundary, the YDB. This has got, I think, 150 radiocarbon ages done by Tom Stafford, who's one of the best in the country. There's the boundary. There's a nanodiamond peak. And we also have a peak in aciniform soot which is Wendy Walbach's work. She worked on the Cretaceous, her PhD was on the Cretaceous tertiary boundary evidence for biomass burning and the observations of acidiform soot associated with the Cretaceous tertiary boundary. We have a similar thing in the YDB, and that's her. Those are her analyses. She's probably the world expert on working with that particular material. But there it is. It's all happening on a razor blade right there. We went to Greenland. We thought we could not get access to grip and GISP ice cores. We probably couldn't, but so this is the poor man's work of ice core work, of ice, Greenland ice. We went to the margins. There's Gerald Haag from Zurich, me. There's the ice core, there's the sequence, there's the glacial, it's dusty, you see, dusty, clear, glacial, Bühling-Adlerud, Younger Dryas, Holocene. And without showing the sequence, we published on this, there's reprints over here. There's a beautiful hexagonal diamond. They were spherical in Greenland. There's an EDS on it. And there's the Greenland. There's the Greenland hexagonal diamond there. There's a beautiful Greenland twinned N diamond. It's called an N diamond. It's another allotrope of diamond. Beautiful twin structure. And there's the atomic lattice in that twin diamond. That's out of Greenland ice. Beautiful stuff. The angles are critical for identifying the particular crystal. Incidentally, N diamond was discovered artificially by the Chinese. They produced N diamond. They named it. It's called N, meaning new diamond. We were the first to discover N diamonds naturally in this work. Nobody had ever found N diamonds before our work on the YDB. It shows you how the research kind of spins off. And then there's the independent verification of diamonds in Lommel, Belgium. We'd worked on the Lommel section and found a peak in these exotic materials. And then Tian went in and they independently verified the presence of, in fact, cubic diamonds. They identified a peak in cubic diamonds right there. See the black layer there? That is the classic 12.9 or 11,000 radiocarbon age base of the so-called Younger Dryas cooling in Europe, which is the prototype area for the Younger Dryas. Okay, now I'd like to spin along and talk about, just show you some pictures of images of these lovely magnetic spherules, the cosmic impact spherules. And the main thing is that they form at high temperature from molten material. They undergo rapid quenching, and this rapid quenching produces this particular texture. And so there's been a lot of misnomers about spherules. Spherules can be formed in about 6 different ways. And the workers who go in and study spherules and don't do SEM and EDS work are just guessing that they're dealing with cosmic impact spherules or not. You have to do the analyses correctly. And we have, and these are some classic fishbone or dendritic patterns in YDB spherules. There's some lovely ones there. You can see this. That's a pretty classic YDB cosmic impact spherule. It was molten. It quenched rapidly from high temperature, molten material. And we find these widely in the YDB in the northern hemisphere. That one there's a aerodynamically shaped spherule. This one's quite interesting. This is from Mexico, Lake Cutzillo section at the YDB. And this spherule has impacted that one. You can see the tectonism, you can see the tectonic ridges that have arisen as a result of those aerial impacts. When these are forming, it's all chaotic. It's total chaos. There's actually the light microscope rendition of that there. And these are not showing very well. In fact, the light is not really bringing out the beautiful characters of these things. This is work of Malcolm Lecomte in the East Coast sections. This is in Topper, South Carolina. Sorry. This is Blackwater Draw. This Topper in South Carolina, Blackwater Draw in New Mexico. That's the classic section for the Clovis, and this is Pawpaw Cove in Maryland. And all of these are just clear impact spherules, and all these are found exactly in the YDB layer.
Jim, are the scales the same for all of those images?
Yeah, pretty well. Yeah, I think so. This was actually Malcolm LeConte's independent work. There's a reprint here, but it's not. We weren't authors on this. This was an independent verification during this argument, ever increasing arguments that occur or debate about this, whether our spherules were impact spherules or not. He went in independently with his own group and verified it. I would say they're all the same magnification. They're being made all to the same magnification. And also we're getting melt glass, high temperature melt glass in numbers of locations, not all of them. We have 3 principal locations. This is the Melrose in northern Pennsylvania, close to the boundary, the border with New York. And so you get all sorts of beautiful characteristics showing there's actually little impact pits in these materials themselves, flow lines and so forth. Rapid quenching, high velocity impacting high temperatures greater than 2,000 degrees centigrade based on the geochemistry. And I could go on and on. There was a paper published, it's actually Bunch and Prep. This is an old slide, it's actually published in PNAS last year, and there's a reprint over here. And not to bore you, but basically, again, this is in the Bunch paper. The geochemistry is very important because you have to do the geochemistry to determine whether these high temperature materials are just floating in from space as cosmic debris, or if they are produced as a result of high temperature impact with the Earth. And I show this one first because it's just simply showing that the YDB geochemistry is similar to known impact crater material and of just regular superficial rocks on Earth, which confirms that this is not cosmic material accumulating. This is actually as a result of terrestrial impact. And again, the temperature diagrams, the petrological temperature diagrams here with the plots of the different spherules. Each one of these are spherules, and so there's different compositions, as you will see. And the main point is that the temperature, you won't be able to see the temperatures probably from the back or the front even here, but basically the temperatures are in the order of 1,800 degrees up to about 2,000 degrees centigrade when you start to add in calcium. You get some of these spherules that are very, very high in temperature. And that goes for some of the glass materials that we have. And sure enough, like the nanodiamond datum, we've got this beautiful spherular datum. This is 18 sites from Western Europe, Northwestern Europe, North America, Mexico, so forth. Most of these are in the US and Canada. There's the YDB. It's marked by a peak in magnetic cosmic spherules of the type I've just shown you. Again, showing that we can imagine volcanic layers deposited as a result of volcanoes, and you can trace the ash layers, the volcanic ash layers around. This is equivalent, except it goes far broader than the material that comes out of a volcano, because this is a much bigger event. Now, this is some stuff we're writing a paper on right now. I'm doing this with Ted Bunch and Alan West and others, and it's pretty unique because we don't know of any other impact event that has this same material, similar material. This is actually from Abu Huraira in northern Syria on the Euphrates River. It's a section that is loaded with malt material. I have a sample up here if you want to look at it later. This one sample from Abu Huraira. It's a very famous archaeological site, dated exactly at 12.9, and it's loaded with melt materials here and spherules. But it also has bone material. This is bone here. That actually is bone. And then on the bone are these aluminosilicate splatters of different compositions. And there they are. So those are aluminosilicate splatters on the bone from this particular impact associated with the YDB. And there also is some, so we're now talking about this exotic biotic materials. These are imprints of reeds. The Euphrates is well known for its reeds. That's a aluminosilicate high temperature blob that's been thrown onto the reeds. What happens? The reeds are imprinted, so you get little etchings, if you like, and it's loaded. Those samples are just loaded with this exotic material. There's nothing like this known from, for instance, the Cretaceous Tertiary boundary. It's totally novel, and it's one of the beauties of working with such a young impact event, because the stuff is so beautifully preserved. Look at this here. This is actually, I've changed my mind, it's not a pseudomorph. These are actually imprints of the vascular material of the reeds. We think they're reeds or grasses. This is the phloem. You've got xylem and phloem tubules here. So this is the internal vascular system. See these little things up here? Those are stomata cells. All this is in silica. It's all silica, and it's all as a result of this molten material coming in and hitting the reeds and transforming, making imprints, immediate imprints of the plant cells in these reeds. It's quite remarkable. We're writing a paper on this. We're well advanced in getting this out because it's so novel. We've never seen anything like this, and nobody else has seen anything like this. Okay, biomass burning. I've got to finish off. Basically, the main point is, yes, we do have evidence of major biomass burning, without going into the details, at that peak at the YDB or close in the early part of the Younger Dryas. Various lines of evidence. This has been disputed, but we stand by our observations of episodes of major biomass burning. This was in the Greenland ice sheet. This is Paul Majewski's work, as one of our co-authors. And there's the ammonium peak. There's the ammonium peak right there at the onset of the Younger Dryas, as measured in the Greenland ice sheet. That's the largest ammonium peak in the Greenland ice sheet in 110,000 years. There's no other larger peak than that. So something pretty remarkable happened at that time, as measured in these various sections. This happened to be the Greenland ice sheet. Ammonium and nitrates are a product of major biomass burning. If this is the case, that there was widespread biomass burning, you would expect to see large-scale changes in vegetation, and that indeed is what is the evidence that we see. This is Perrose's work, Perrose, published in 2008. Without going into the details, you can see here, there's the onset of the Younger Dryas, in there. And this is a plot of Picea or spruce over eastern North America. And basically, the spruce, based on this evidence, were essentially decimated in eastern North America, based on this data. And then they came back later in the Younger Dryas. So there's the spruce decimation, if you call it that. The spruce was widespread vegetation in eastern North America at that time. It was replaced by, what was it replaced by? In eastern North America in particular, although it's a little bit more general throughout North America. It's replaced by populus. This includes poplar, cottonwood, and aspen. There's the peak, the early Younger Dryas peak in populus, which is a early succession form following wildfire. It's well known for it biologically, disturbance taxa, and so forth. And then the spruce goes back. The populus goes back, and the spruce comes back again. And so finally, the human evidence as well. You've heard about the Clovis people. The Clovis people were well distributed in the over North America in the late Allerud. There's about 400 years. The Clovis were well distributed. They left their distinct toolkit. throughout the continent. Or what happened to the Clovis people? The Clovis culture essentially disappeared right there at the Younger Dryas. So this is basically the termination of the Clovis culture. Obviously humans survived, but the Clovis culture didn't with this particular toolkit. And so there was a major cultural turnover. These were successively replaced later by other Stone Age cultures of North American Paleo-Indians. And so what happened to we've written a paper with David Anderson, which is again over here. David Anderson is he's in charge of the North American artifact collection in Tennessee. He knows artifacts and the quantification of artifacts more than anybody. And he's long suggested that there was a major decrease in the abundance of artifacts, human artifacts, all over the continent at the onset of the Younger Dryas, as suggested here by this histogram. So this suggests itself indirectly that there was a population drop of North American Paleo-Indians at the onset of the Younger Dryas, and then they came back later on in the Younger Dryas, towards the end of the Younger Dryas. This is a similar story in California with Terry Jones's work. And but this really one grabs you, or grabs me. This is This is in the paper by Anderson. A lot of the stuff that I've talked about is published. Some of it isn't. I'm trying to give you an overview. But basically, for Eastern North America, there were about 11 known major stone tool quarries. These were the factories for the Clovis people. And this is where they were absolutely relied on these quarries for their tools. This was crucial, as you can imagine. Our tools are crucial. And so what happened? Of course, you got very good archaeological records at all of these places, or most of them. So you can date them, you can see when things happen. And look what happened at the onset of the Younger Dryas. Basically, the tool making stopped. The tool making stopped of these stone tools by the Clovis people in the early part of the Younger Dryas, and then it came back later on in the sequence in the later Younger Dryas with successive Paleo-Indian cultures. So the people went somewhere. Who knows? Maybe they came down to Florida to escape the weather or something. I don't know. But they left those quarries. So anyway, the sort of the grand finale, if you like, if you don't believe anything I've been telling you, I thought I'd leave this to last, because this is only a week and a half old. There was a conference of the Lunar and Planetary Society conference in Houston. They have an annual conference of the impact people and so forth. And they presented this. It's a paper by Petiev. It's a Harvard group, totally independent group. And basically they presented this just a week and a half ago in Houston. And this is really like an analog for the KT boundary where they found the Iridium Peak. They were looking for an Iridium Peak in the Greenland Gisp ice core. They've been working on it for years, but it took a long time to get the stuff analyzed, it seems. Anyway, so here they presented this, and what they've discovered is this remarkable platinum peak right there, exactly at 12.9 thousand years ago in the Greenland ice core record. There it is. It's about 1,000 times above average background, and this, they accept that this is conclusive evidence of a major cosmic impact with Earth at 12.9 thousand years ago. And so they didn't find the Iridium Peak, so there's a lot more work to do. There's questions, why didn't they find an Iridium Peak? Because we actually have above background, small above background increases in iridium, which has been independently confirmed by numbers of workers in different locations. It's not a KT boundary Iridium Peak, but it's above background, it's there. And we're so curious why they don't find an Iridium Peak. There's lots of questions. These were very small samples they had available to run the analyses. But there it is. It's about a 25-year rise and a 7-year fall. There it is in the linear scale. And so this, sure, unless you want a video of these impactors coming into Earth, I can't provide you with that. But I can provide you with this line of evidence, including the independent lines, particularly this Petya work has just been published. They, in fact, have a paper I know this because they sent it to me. I can't show you the paper because it's under review currently with PNAS. And they title this, "A large platinum anomaly in the GISF2 ice core points to a cataclysm at the onset of the Younger Dryas." So that basically is their title of their paper. They hum and ha obviously about what kind of an impactor it was. It's a highly differentiated one. So the question is, why is there no iridium? This is very unusual. But then, much about the Younger Dryas has always been unusual. So there you have it. And so, where did it occur? We know where it occurs because they've dated these green-lined ice cores almost to annual resolution, which is, of course, the beauty of this discovery. We don't have that kind of resolution. We say plus or minus 100 years. They can say plus or minus 5 years or 1 year. That's how good it is. And there's the Younger Dryas as long determined. There's the Younger Dryas onset. This is the work of Severinghaus and Alley and others. There it is. And there's the platinum peak. It's right on it. The date they give for the platinum peak is 12,890 years. 12,890 years is the date they give to that platinum peak. Have it. And this is plotted against nitrate. This is something that was from Paul Majewski's work. This is nitrate. This was published years ago. And there's the big increase. There's a big step up in nitrate, which begins there, right at the platinum peak. It steps up. There's obviously some oscillations, and it just keeps stepping up and stepping up. And there's several decades. There's the peak. It's one of the largest peaks in the Greenland ice sheet. There's the nitrate. So what this is suggesting, if indeed this is reflecting biomass burning, it suggests that there's biodegradation as a result of this impact. And then there's a lot of dead material around, it accumulates, and the fires just increase. It's not just simply an impact, and everything, the whole world, the whole Earth bursts into flames. It's not like that at all. It just produces a lot of fuel that increases in that very early part of the Younger Dryas. And actually then it stays, interesting enough, which is actually a very interesting observation. So finally, Amelia, you can see this is a very integrative challenge and campaign, really. And it's hard to get across in 1 hour. But anyway, so basically, as far as the Younger Dryas cooling onset is concerned, it's enigmatic. The timing is at high insolation, unlike other terminations. There's an exceptional North American plumbing shift in freshwater flow. There is evidence of freshwater outbursts broad in the Arctic region and in the North Atlantic around Greenland, and even through the St. Lawrence with Tom Cronin's work. And believe it or not, the switch over from the freshwater of Lake Vermont to the saltwater of Lake Champlain of northern Vermont, that was a big switch over during the deglaciation. Guess when it occurred? Within a year of the Younger Dryas at 12.9. That's when when Lake Vermont finally became saltwater. That's when the ocean came in to Lake Champlain. And that's Tom Cronin's work. So there was a major ocean circulation change and the carbon perturbation that I haven't talked about. There's a close association with abrupt continental scale ecological reorganization, biomass burning, vegetation disruption, megafaunal extinctions, and human adaptive shifts in population decline, as I've talked about. The YD onset coincides with YD layer containing proxies of cosmic impact origin, nanodiamonds, impact-related spherules, platinum, melt materials. And the data is consistent with the low-density cosmic impacts over North America and elsewhere, triggering YDB events and processes that we call the YDB Impact Hypothesis. So thank you. Any questions? Yes.
That was masterful. It was a masterpiece.
You mean I got a PhD from that one? At USF? Oh, I love it. Can you give me a certificate?
Do you think that the explosions caused the ice sheet to fracture?
That's a hard question. I've thought about that, but I don't think so. I think there's a destabilization around the edges, and there may have been some subglacial instability. See, we don't know. I mean, basically, there's been a big question: is where? I mean, we've argued for major multiple impacts that are mostly aerial, because otherwise, where are the craters? Well, I could show you a crater, but there actually is a crater that's been found that's dated to 12.9 in the St. Lawrence. It's only 4 kilometers wide. 4 kilometers. It's the biggest one in the Americas since 35 million years. So, there's action, but, there's debate about its exact age. They've caught it, and believe it or not, the youngest sediments, the sediments that start accumulating on the crater date to 12.9. So, but there's still debate about what the age is, and they haven't published, they haven't committed themselves other than abstracts. But anyway, the question is whether there was any major impact that hit the ice. The evidence that we have suggests, when you look at the size of spherules, suggests that the epicenter, if you like, of the impact was over the ice sheet, in which case there's not going to be much evidence, and potentially no major crater, because it would be attenuated during forcing through the thick ice sheet. So all those are questions. It's just hard to answer those questions. It's very early. I mean, this opens up a whole spectrum of questions like that. But I'd love to know. I'd love to know that answer.
We're going to take one or two more questions because we're going to try to
Yeah.
get together before dinner.
Yeah.
We're going to take one more question, then we have coffee and some goodies.
Sorry
Jim
about
is
that.
going to be here
Yeah.
the whole time. He's not going to disappear. So
Yeah,
there's
right.
plenty of opportunity to give
I'm happy to
We
talk
wanna get
to you
out
and show you
there,
materials, whatever you like. I'm happy to do that. But anyway.
One more question.
Was there a parallel European universe as far as megafauna, as far as human?
Yeah, good. Yeah, Eurasia is a much more. It's a huge continent. It's the evolution. The megafaunal extinctions in Eurasia are more complicated. It's quite clear. The humans were there much longer. There's a much clearer, greater complexity of extinctions in the megafauna in Europe. There is some evidence, yes, that there was some. The great deer or the Irish elk in Ireland, guess where it dates to? It disappears in Ireland at 12.9. So, and that's an isolated island from Eurasia, but it did disappear at 12.9. I've talked with them and I've seen their materials in Dublin. So there is some evidence, but it's much more complex, I think, in Eurasia, because it's such a continent. As far as the human effects in northwestern Europe, they've long argued that there was a major population decrease in humans in Western Europe at the onset of the Younger Dryas, including Spain, which is south in Europe. They say, why are the Americans arguing about a population decline and the onset of the Younger Dryas? We've known that for years. So just to put that in perspective, it's called the Magdalenian cultures, which were the cave painters. Believe it or not, the exquisite cave painting of Europe terminated at the onset of the Younger Dryas. They went into the Dark Ages culturally. Yeah. And that was the disappearance of the Magdalenian, which is equivalent to the Clovis. So there's some parallels, yes, but it's much more complicated.
come back, it's around 250 little plus. We'll be back around